analysis. Okay, so when we talk about correlation, we talk about regression analysis. What we're trying to do is we're trying to discuss and explore the relationship between two things, two variables. Uh, so far through the class, up until this week, you've only studied one variable. You know, what's the average jackpot of a lottery? What's the average salary of a nurse? Things like that. But now what we're looking at is we're saying, well, are two variables related to one another? And I proposed here uh, uh, the population of a city and the number of public schools in that city. Are they related to one another? And we use the idea of correlation to help us sort of conclude or have an understanding as to whether there is a relationship and whether it's a strong relationship, a weak relationship. So here I collected some data. I picked some cities just at random: New York, Chicago, Houston, LA. You'll notice that these are the 4 largest cities in the US. I also picked New Orleans because it's an interesting city for reasons I'll tell you about in a second. And then I picked a random Naples, Florida. I don't know why. I could have picked anything. So what I did is I went to go identify their population, and it's measured in millions. So New York is 8.63 million people. New Orleans at 0.392, that means 392,000 people. Then I looked at the number of public schools, 1,700, 600, so on. New Orleans is kind of interesting. Look how low it is, 78. We'll talk about that in a second. Okay, so correlation, I'm going to erase these. I forgot to erase these from last year. Okay. Okay, correlation just tells us whether or not there's an indication of a relationship. It doesn't mean that there is, in fact, a relationship. It just means that there could be a relationship, or a candidate for a relationship. So correlation sort of measures the strength of the relationship, if there is one. And so correlation, there's a couple of different characteristics that we want to talk about with correlation. So let me change my color. We use the variable r for correlation, a little r. And r can be any value between -1, it could also equal -1, and +1. R, that's it. That's the bounds of 1. The bounds of r, the correlation. The closer to 1 it is, as r approaches +1, we call that a strong positive correlation. Similarly, if r approaches -1, that's also a strong correlation, but it's a strong negative correlation. And the closer that r is to 0, we say that it is either weak, or if it's equal to 0, no correlation. No correlation. I'm going to finish it there. So the closer to the end values you are, the closer to 1 and -1 you are, the stronger the correlation relationship. The closer to 0, the weaker the relationship. Okay, so what do we mean by strong positive and strong negative? What does that mean? Let me erase this. Okay, so when we say strong positive means as one variable goes up, so does the other. And as one variable goes down, so does the other. Okay, as one goes up, the other one goes up, or if one goes down, the other one goes down. That's what strong positive means. The variables move in the same direction. And you can identify a strong positive correlation in a graphical nature if the graph points up. If the graph points up, that's a strong positive correlation. Okay, so we can see here that my graph is a strong positive. Okay, so what would be an example of a strong positive? I have one already here, population of the city and the number of public schools, but think about other strong positive correlations. The temperature outside goes up, your cooling bill, your AC bill also goes up. That's a strong positive. They move in the same direction. Or if you work more hours at your job, you make more money. For those of you who are for people who have hourly jobs, more hours you work, more money you make. Things like that. So it moves in the same direction as well. Strong positive, on the other hand, is the opposite. Strong negative means as one variable goes up, the other goes down. The other goes down. Okay, so what would be an example of that? Think about the cold snap we just had last week. As the temperature went down, your heating bill went up. So they're moving in opposite directions. The more money you spend, the less money you save. So they're moving in opposite directions. So that's what strong negative means. And you can see that in a graphical sense if the graph moves downward, if it's angled downward. And no correlation happens whenever it's sort of scattershot. And to see a no correlation, you would look for dots just all over the place. So let me also mention that when you're looking at a graphical, you're turning your data into a graph, you're not going to see the dotted line here necessarily. What you're going to see is the dots. Notice the dots are arranged in a linear fashion, angled up. And so because the dots are angled in a linear fashion, that tells you have a positive and maybe a strong positive correlation. If they were angled, if they were clustered downward, then it would be strong negative. And if they're just sort of scattershot all over the place, no discernible pattern, that probably means you have no correlation. Okay, so that's what correlation is. It just says you have a possible relationship, and the relationship is either weak or strong, positive or negative. That's what correlation is telling you. We can calculate it as well. We're talking about strong positive, strong negative, or a weak, but what is the number actually? When you're looking at data, say like this, I can't tell what the correlation is. I have a good sense that they're moving in the same directions because if we notice as the population goes up, look at the number of public schools. Yeah, it tends to go up too. So so it looks like it's a strong positive correlation, but how do I know? Well, the way that you know is you would calculate it. And we can calculate it here using Excel. And you would want to use Excel, by the way. You can do it by hand, but it is very tough to do it by hand. I recommend doing it in Excel. Put your data in Excel and use the formula. So equal sign, because we're telling it a formula. And the correlation formula in Excel is CORREL, correl, for the short for correlation. So hit that function, hit that formula, opens a parentheses, and you'll notice here it says array 1 and array 2. So what you have to do is you have to go to the top of your first data set, click it, colon, bottom of the first data set, comma at this point. And now top of the second data set, colon, bottom of the second data set, close parentheses. So top colon, bottom, comma, top colon, bottom, close parentheses. Boom. So this is 0.97. Remember we said the closer we get to 1, the stronger the strong positive correlation. And so this is telling us there's a pretty strong positive correlation. So it suggests that it suggests that there may even be a causal relationship. It suggests that, yeah, the more people you get, you're going to have to build more public schools within your city. And does that make sense? Let's sit back and think about it a little bit. No math. Let's just think about it. As a population goes up, you have people of all different ages: elderly, middle-aged, young adult, and then kids. Well, as that population increases, though, you're having an influx more of people with kids. And so they're bringing their kids into the city. And so you have more people with kids. And so you have more kids. And so then you need more schools. Now, is that always the case? Well, no, because it depends upon how many kids that those families have. Not everybody has 3, 4 kids. Some couples have no kids. Some couples have one kid. Some couples have more. So, it doesn't always mean that, and that's why it's not a perfect one. Correlation of one is because not every couple has the same number of kids, or not every couple has more than 2 or 1, has any kids. So it's not a perfect correlation. It's not, and when we say perfect, we mean either 1 or -1. It's not perfect correlation, but it's pretty darn close. So it does make sense. It does make sense to us. Now, there's also another, if you're thinking about variables and factors that could be affecting your analysis, is take a city like New Orleans. Take a look at New Orleans. It has, and the dot for it is right here. The dot for it is right here. It, no, yeah, yeah. No, sorry, that's not it right at all. It's right here. The dot for it is right here. Notice it's the thing to take note of is it's below the line. So what's going on here? And take a look at Houston. Houston, by the way, is 2.3 million, 284 schools. It's also significantly below the line. What's going on here? Is there something going on in the city, something unique about those cities that is causing it to sort of deviate from the sort of average, if you will? And what's going on? And I pick on New Orleans a little bit because of its history. Remember in 2005, sort of getting on now, but in 2005, there was Hurricane Katrina, and it just wiped out the city. But what it did in the aftermath is the public schools did not reopen. For many years in New Orleans, there were 0 public schools. They went to a charter school system for many years. And that charter school system has sort of hung on in New Orleans. And so that's why you have such a low number of public schools, is because most of the schools now in New Orleans are, public schools at least, are charter schools. And so they're kind of a hybrid model, not really public, not really private. And so my point is that another reason why you could have a strong correlation but not a perfect correlation is because there's other variables going on in the background. And that's what that means is the only time you will have a perfect correlation, either 1 or -1, is if it follows a formula. Otherwise, most of the time, 9 times out of 10, you're going to get a correlation that is not perfect. And so what this means is that the number of public schools in a city is mostly determined by the population, but there could be other factors as well, because it's not equal to 1. There are other factors at play. That's sort of what you know, or what you can sort of surmise from this. Okay, one thing to also note about correlation is that even though we have a strong correlation, it doesn't mean causation. What does that mean? The data indicates that there's a strong relationship, but it doesn't necessarily mean that the increase in population will cause you to increase the number of public schools. Take, for example, a city that has just a ton of elderly people. Oh, say, Naples, Florida. Something like that. I don't know, actually. But think about Florida. A lot of retirees go to Florida. They don't have kids. They don't have school-age kids. And so the increase in retirees will not lead to an increase in public schools. So the point is suppose you get suppose you have a city like that, and you're sitting back and you're saying, man, our population is very high, but we don't have public schools. It's, well, because we have a lot of elderly. We have a lot of couples who don't have school-age kids, elderly, 50s as well. They don't have school-age kids. So, so the point is don't assume that a strong correlation means that they are in fact related, because it could also just be a fluke. It's just something, it's just something that happened, a coincidence. The whole point of that then, if correlation does not equal causation, then what's the point of studying correlation? It's because correlation gives you sort of an area of investigation. It says these 2 variables may be related. So go study that a little more. Go study to see if there's a causation or causal relationship. If there's no correlation, then that means don't waste your time on it. You don't have to study it anymore. So where would this be helpful to people? Well, take doctors, and they're trying to understand the relationship between, to say, age and cancer risk, or gender cancer risk, hereditary genetics and cancer risk. So they're looking at correlation and saying maybe there's a link there, and we'll go study that to see if we can prove it or not. So it's suggestive of a link, but it doesn't mean that there is in fact a link. It just says you got to go do more analysis. That's all that means. Okay, so the other thing here, that's correlation. And the other part of it is regression analysis. Now, when you do the data, you can then do regression analysis to make predictions about the line, make predictions about your data. So suppose you have a city like I don't know, Lexington, Kentucky. Lexington, Kentucky. I don't know their population, but I'm going to guess it's about 500,000 people. Big city, but not a huge city either. 500,000 people. So we have 500,000, it's right here. But notice it's not a date, it's not a dot on the map. We don't know what it is. So what regression analysis can do is it says, okay, well, you have a study. Can I take the study and apply it to my circumstance? For example, you're on the school board of Kentucky. You're on the school board for Lexington, Kentucky. You see this study out here on the relationship, the correlation between population and public schools, and so you ask yourself, do we have the right number of public schools for our population? That's what regression analysis can do. It can give you sort of a predictive measure to say, here's where you probably will land. Doesn't mean it's going to be exact, but you're going to be in this neighborhood, close to it. So if we're Lexington, Kentucky, based upon the data, what would be the number of public schools? So you could do it graphically by going up to the line and moving over. So it's suggested about 200. But if you wanted to be perfect with it, this right here is what we call the regression equation. And so X, that's the X-axis, remember, and this is the Y-axis. And so in this example, the X-axis represents population. The first column of your data is always your X-axis, population. The Y is the number of public schools. So if I take this equation, Y equals 195.16x plus 46.718, and I plug in my population in for X, it'll spit out the number of public schools that it predicts. So that's what I'm going to do. Y equals and so what? Equals what? 195.16 times 500,000 plus 46.718. So it tells me I should have about 144 public schools, or 145 public schools. So my graphical estimation here of 200 was way off. Now that I sort of see the answer, I can see I was way off. 500,000 is more right here. So it should have been right there. Yeah. So it makes more sense now. Okay, so that's what regression analysis can do, is it says it can take your data and make a prediction about other circumstances. Now, the limitation of regression analysis is that regression analysis is only good within the maximum and minimum of your data set. That's it. So in essence, if you have a city, let's take, for example, Tokyo. Tokyo has about 13 million people in it. Huge. 13 million is way over here, it's off the charts. The point is it's beyond It's beyond my outer extreme. So it's beyond that window. So my regression equation here is useless. It's useless to Tokyo because Tokyo is outside of my window. So so the point is the regression analysis is only as good as the window. And the window is determined by the minimum data value and the maximum data value. Minimum X and maximum X. But if your data value, if the data value you're trying to predict falls within that window, the regression equation is pretty darn good. It's not perfect. It's not exact because I bet you if you go look up Lexington, Kentucky, how many public schools do they have? It'll be close to 140, 144 or 145, but it may not be exactly 145. It'll probably be like 165 or maybe it'll be 135, something like that, but it'll be pretty darn close. And that's the power of regression analysis, is that it doesn't have to be perfect. We don't necessarily need it to be perfect. It can get you pretty darn close. But notice, it gets you pretty darn close without having to go collect a whole lot of data. And remember, that's the whole point of statistics. Make predictions without having to do a whole lot of work. It sounds like a lazy man, a lazy mathematician's sort of study, but it's just the analysis. The formulas and all that are so good that you don't need a lot of data. A little bit of data can get you pretty strong predictions. Okay, so I hope you found this helpful. We took a look at part B of the project, and we took a look at correlation, and we took a look at regression. Let me know if you have any questions on this, and I'll be glad to help.